Ever stop and think about how the billions of tiny on-off switches inside your phone or your laptop can possibly lead to something as complex as playing a video or calculating a spreadsheet or even recognizing your face? It feels like straight-up magic, right? But believe it or not, it all boils down to one super simple idea. So let's just get right to the heart of it. The big question is this: how does a machine, a thing made of metal and silicon, actually make a decision? That's what we're going to break down right now. All right, let's dive right in. To even begin to understand how a computer thinks, you gotta start with the language it speaks. And here's the cool part. Its alphabet is way, way simpler than ours. You and I, we think in what's called base 10. We've got 10 digits, 0 through 9, and their position matters. The 2 in 200 is worth more than the 2 in 20 because of where it is. It's all based on powers of 10. Pretty straightforward, right? Well, computers do the exact same thing, but they've only got 2 symbols to work with, a 0 for off and a 1 for on. That's it. This is base 2, or what we call binary, and instead of powers of 10, each position represents a power of 2. The 1's place, the 2's place, the 4's place, the 8's place, and on and on. So let's see what this looks like. You want to represent the number 2? Easy. You just flip on the switch in the 2's place. Boom, you get 0, 1, 0. For the number 3, you need a 1 in the 2's place and a 1 in the 1's place. So that's 0, 1, 1. And for 4, you just need a 1 in the 4's place, 100. And just like that, with only 2 symbols, we can build literally any number we want. All right, so positive numbers, they kind of make sense, right? But what about negative numbers? I mean, how do you even show negative with just a bunch of on and off switches? Well, it turns out computers have a really slick and standardized trick for this. And that trick is called 2's complement. Now, don't let the name scare you. It's really just a recipe, a procedure that everyone agreed on for how to turn a positive binary number into its negative version and then back again, using nothing but those same old zeros and ones. Let's actually walk through an example so you can see how simple it is. Say we want to find negative 17 in a 6-bit system. First, you just write out positive 17, which is 0, 1, 0, 0, 1. Step 2, you just flip every single bit. Seriously, every 0 becomes a 1 and every 1 becomes a 0. And for the grand finale, you just add 1 to that result. And just like that, 1, 0, 1, 1, 1, 1 is how a computer sees negative 17. It's a totally mechanical process, which, is perfect for a machine. Okay, so here's the really crucial part. Once a computer has its language for numbers, it needs a grammar, right? It needs a set of rules to actually do things with them, to make decisions. And that's where this thing called Boolean logic comes in. It's basically the math of true and false. The absolute simplest rule is the not operator. And it does, well, exactly what you think it does. You give it a 0, which is false. It spits out a 1, which is true. You give it a 1, you get back a 0. That's it. It just inverts the input. All right, next up, we've got the AND operator. Just think of this one as being really strict. The output is only true, or 1, if input A and input B are both 1. If even one of them is a 0, the whole thing is a 0. No exceptions. And then there's the OR operator. This one's way more relaxed. The output is a 1 if input A or input B is a 1. It doesn't care which one, or even if they're both 1. The only possible way you can get a 0 is if both inputs are 0. So there you have it. Those are our basic building blocks. Now, here's where it gets really powerful. What happens when we start chaining these things together? Well, it turns out, with just not, and or, you can literally build a formula to solve any logic problem you can think of, no matter how complicated it seems. Just take a look at this truth table here. We've got 3 inputs, A, B, and C, and this one output, S. So how can we describe what S is doing? We can actually write a perfect logical equation for it. And the method is surprisingly simple. You just go down the list and find every single row where the output S is a 1, and you write an AND statement that describes that specific row. So if you go through and write a little logic statement for every single row where the output is 1, and then you just mush them all together with ORs, you get a perfectly accurate description of the logic. But, look at that thing. It's a complete mess, right? It's technically correct, sure, but it's long, it's complicated, and trying to build that as a physical circuit would be a nightmare. And that's what brings us to a really brilliant little trick for optimization. Because in the world of computer hardware, simpler is always better. It means faster, cheaper, and it uses less power. So the big question is, how do we clean up that messy equation? And wow, here's the power of simplification right here. On the left, you've got that long, ugly equation we just built. That little bar over a letter just means not, and the plus signs mean or. It's a mouthful. But after you work some logical magic, that entire expression boils down to what you see on the right, S equals not C. That's it. The output only cares about what C is doing. That is a massive, massive improvement. So how on earth do we find that super simple answer without doing a bunch of painful algebra? Well, the answer is this really clever visual tool called a Carnot map, or a K-map for short. Now, I know it looks a little weird at first, but it's really just our original truth table, but rearranged into a special grid. And this new layout is specifically designed to make patterns just pop right out at you. The real magic here is that any ones that are touching, either up and down or side to side, they represent parts of our messy equation that we can simplify. So let's do it. Let's group all the adjacent ones on our map. See those two big groups I've circled? Now look really close at what's happening inside those groups. As we move from one to another, what's going on with A and B? Well, their values are changing all over the place, right? Sometimes they're 0, sometimes they're 1. But what's the one thing that stays exactly the same for every single one on this entire map? It's that the value for C is always 0. That's the hidden pattern the map reveals. It's telling us that the output is 1 only when C is 0, and it couldn't care less what A and B are doing. In other words, the entire complex logic simplifies down to one beautiful thing. S equals not C. And really, that's the whole ballgame. It all starts with a simple binary alphabet. Then you add a clever trick for negative numbers, and you combine it with just a few basic rules of logic that can be simplified down to be super efficient. Every single complex app, every video game, every AI we have today, it's all built on these few simple rules of true and false. So the next time your phone does something that feels like magic, you'll know. You'll know it all started with a simple question of 1 or 0.